I don't know if I'll finish it today, but we'll definitely finish it on Wednesday. But I'll give you a homework over 8.1, 8.2, and 8.5 all at the same time. We're going to do 8.5 today. All right. So are we good with the contingency table stuff, or should we do another example? I don't care one way or the other. We good? Okay, that's fine. I guess you'll find out when you try to work on your homework. If you're not good, you can always come ask me a question. All right. Let's add a page. All right. Well, let's do then this last bit that we're going to do on hypothesis testing, and then we're going to go into some more of the theory behind it. So today we're going to talk about hypothesis tests for the median, and as I drop everything everywhere. So this is what's referred to as the Wilcoxon tests. All right, so the stuff that we've done before have all had some sort of normality assumption to them, where the normality assumption allowed us to change things, especially in the last couple of sections. We had the binomial assumption, that we did the normal approximation to the binomial, and from there went to chi-squared and did chi-squared testing, right? In both of those cases where we did in the first two sections, right? So today we're going to get rid of that assumption of normality and start doing a test on the median. So this is, the median is not really a parameter of a distribution. It's not going to determine what the distribution is necessarily, whereas the mean or whatever else is going wrong. So what this is, the test that we're going to do today is referred to as a non-parametric test, doing a test on the median rather than a parameter of the population. You could do similar testing for other percentiles of the population if you really wanted to. I'm not sure that anybody ever does, but you could do it, theoretically. By the way, there's a whole chapter, a whole section on order statistics. We've talked about order statistics last semester, where you talk about taking the sample and putting them in order. We did the max and the min in particular. But it's a matter of doing the PDFs of those, is a matter of going back to your first principles of finding the distribution function, treating it as a binomial problem, and then taking a derivative. So as far as the order statistics go, we've done enough of that that I'm not going to go through the 8.3 or 8.4. That was what 8.3 and 8.4 were doing. We're giving 8.3 was talking about doing this order statistics, which you did last semester. 8.4 was doing confidence intervals for those things. So finding confidence intervals for, say, the 40th percentile and those kinds of things. Which, if you can do confidence intervals, of course, then you could do hypothesis testing. I mean, confidence intervals are essentially the same thing. So, all right. So to do this, let's just do a specific example to start with of what this, what these different statistics are. Excuse me, these different hypotheses are. So, to that end, I guess I probably should have loaded this up first. Oops. What's that? Oh, that's true. Since it was just on there, yeah, I guess I should probably change my password now. So what you're saying is I need to definitely want to change my password after class. I didn't really think about that being on the screen at the same time. Oops. Really wasn't thinking about that at all. Well. Especially if you can go back and watch it. You can definitely go back and get my password. Yeah. Yeah, I'll be changing my password. Didn't really think about that. I'm glad somebody said something. Appreciate that rather than just hacking into my account. Submitting final grades for everybody. You know, those kinds of things. On second thought, maybe I shouldn't have said it. All right. So this is just problem number 1 on page 451. Really wish I would have thought about that with the password. I really want to change it. All right. So the idea here is to do a hypothesis test to see if the median weight of certain loads of candy, it really is 40,000, I'm assuming pounds, yes. All right, so here's how we do this. So the first idea behind this is to use what's referred to as the sign test. So all we're going to do here is assign a plus or a minus, depending upon whether or not this is bigger or less than the median. So it's going to be a +1 if it's above the median, a -1 if it's below the median. Okay? So in this particular case, we're trying to test to see if it's underweight, essentially. Is it less than 40,000? So probably I could type it in, but probably the easiest way to do it is to use what's referred to as the sine function. And I'm just going to take the sine of this thing, the 41,195, and subtract 40,000. And then copy that down. All right. So the only reason why I'm doing this is if you, I mean, we could have counted it just as easily to do this, but we're going to use that sine function here in a little bit for the other type of tests we're going to do. And it's just as easy to do it this way to count it versus counting it by hand. You could also have done a count if and did a count if in a condition. But anyway, so this gives you, it's +1 if it's above the mean, or excuse me, above the median, the 40,000, and it's -1 if it's below it. So what we want to count for this particular statistic is how many are below the 40,000, because that's how many it asked us for, or what, I'm sorry, that's what the hypothesis asked us to check. So I'll do a count if, and I'll highlight the array, and then type in -1. So 9 out of the 13 are below the median. Oh, yeah, sorry. Why does everybody have to ask me every time? Because I never remember. Sorry about that. My apologies. All right. So 9 out of the 13 values are below the median here. Now, our question is that abnormal? I mean, that's the whole idea of the hypothesis testing, right? We took a sample. We're trying to see if we take the sample, is it abnormal to what we think the null hypothesis is? We always compare it to that. All right, so we think that the median is 40,000. So we would expect, since that's the median, if we take a sample, approximately half of them should be below, approximately half of them should be above, right? That's what we would think. So for our purposes, we would think of that, if we do a just a sample, we should think that's binomial. If we're randomly sampling this, there should be a 1/2 probability that we pick one below the mean or 1/2 above the mean, right? So if we've got a sample that should be rare, at this point 9 out of the 13 are below the mean, is that rare compared to what we should get out of the 13 for the median? So if we want to calculate a critical value, and I think this problem probably told us to do a 0.05 significance on it. Where is it? It doesn't say. I guess just say alpha equal to 0.05. So we would want to know how many below the mean would be considered too many below the mean at 0.05. Okay. So to that end, let's see if we do binomial distribution. My binom.dist here. Notice it says number is S, and the number of trials, and the probability of the success, and then the cumulative, whether or not we want it cumulative. So the number we have is 9. The number of trials here is 13. The probability is 1/2, because there should be 1/2 of them, right? And then cumulative would be true. Because I want to know, basically this is going to give me from 0 to 9. I want to know 9 or more. Is that rare, right? Because that would be a critical region idea, right? If it's rare, it would be a certain number or past that. So we can do 1 minus this after we're done. So up to 9 is 0.95386. So 9, well, I should have done up to 8, shouldn't I? Because I did 9 or more. Let me flip that around, sorry. Let me change this to, instead of 9, let's do 8. Because if I want a p-value, it would be 9 or more, right? The complement is 8 or less. So, or if you think of it from a critical region standpoint, up to 9, well, you would need 10 or more to be less than 0.05, right? Because up to 9 was 0.955 something. I just had it up there on the screen a minute ago. All right, so the p-value for this 9 would be 0.13342, which is definitely not high enough to reject. Do you agree? So that's all we're doing with the sign test here. So just to write this, down, for the sign test, our null hypothesis is that the median, the median is equal to some specific value. The alternative is that it's less than or greater than our critical region will be the set of all y being greater than or equal to some specific y naught, where the y naught, the probability that you're greater than y naught, greater than or equal to y naught, is less than or equal to alpha. And so your y naught here is just the number of successes you need. Success will be defined as either the success is just being on whichever side of your median that you want it to be. So for us, the success was -1 because it was below the mean. So the number of successes was counting the number of negative ones. Right, see if we can do another one here, and then we'll talk about adding in a couple of more statistics. But in this case, we're literally just counting the number of things that, let me write that down. I want to write down. We're just counting number of values in the sample that are below or above the median. It's literally all we're doing on that one. Now, notice what the sign test does not take into account is the size of the particular values in our sample. I don't know why I couldn't get the word out. Notice that it doesn't take into account relative sizes at all, right? All it does is say, above the mean, I'm going to give it a +1. Below the mean, I'm going to give it a -1. If I'm testing below the mean, I'm going to count -1s. If I'm testing above the mean, I'm going to count +1s. And I want to know, is that too many -1s if I'm looking below the mean? Is it too many +1s if we're looking above the, I keep saying median, sorry. Is it too many +1s if we're above the median? Is it too many -1s if we're below the median? And by too many, we do that the binomial probability of successes. Okay. So to do another one that involves the sign test, I believe 8.5-3 also asks you to do something with the sign test. It's part A. So let's flip over to 8.5-3. We want to test whether the median is bigger than 5.9. Now, in this case, they gave you the sample ordered. In the previous one, it wasn't ordered. This one, the sample's ordered, so it's pretty easy to count. But just to practice again with that sine function, I want to test whether each value is less than 5.9. We're going to use the sine function a little bit more importantly here in a minute when we do the next test. So it gives you a +1 if it's above the mean, a -1 if it's, why don't you see mean? Median, and a -1 if it's below the median. So we see that pretty quickly. And in this case, again, we want to add up. Oops. We want to count, not add up. In a minute, we're going to count. We're going to add up. We're going to count count how many times 1 pops up. And guess what I didn't do again? I didn't zoom in. So let me zoom in. And if you need, there's what the formula looked like. Okay. So far, so good? All right. So to illustrate what we mean by the critical region, let's use this binomial inverse function. The binomial inverse, if I give it a specific probability to say, what do I need to get to that probability, it will spit out the number of successes that you need. Okay? So if I use this binomial inverse function, number of trials is 25. The probability of success is 0.5. And then your alpha is the probability you want. In this case, I think we're doing 0.05 again. This is probably going to be small, but that's okay. So this says that I have to get up to, notice it's in reverse. It says I have to get up to 8 before I have a probability of at least 0.05. Right? I have to get up to 8. So we would really want to go the other way around and want to be able to get up to a 0.95 because I want 17 or higher. This is going from the bottom up, essentially. So if I go back in here and change it to 0.9, oh, you can always do the complement, obviously. It says you have to get up to 17 before you get 0.05, right? So your critical region here would be 17 or more. Did we hit in the critical region with our count? Looks like we did. If we do the p-value for 17, we should be able to do 1 minus the binomial distribution of 17, and then number of trials is 25, probability of success is 0.5, and we do want it to true is, oops, that's not the p-value. I think I need to do 16 because I took out the 17, sorry. Because I want 17 or higher. There's the p-value. So actually in this case, notice that the 17 doesn't quite get us what we need. We need to get up to 18. But the p-value here says to be 17 or higher, you're at 0.053. So you're close, but we wouldn't reject. Probably just need a higher sample size to see. So, anyway, does the idea make sense what we're doing? Just counting the number of ones that are above and then checking a binomial probability to see if that's actually a rare occurrence. This is pretty rare, but not rare enough if we're going to use a 0.05 significance level. Does that make sense? All right. So the next test that we're going to do is what's called a sine rank test, or the Wilcoxon sine rank test. All right. So here's the idea behind this. And rather than going through a long-winded explanation of things to start with, let me do another specific example here. So this is 8.5-4. Yeah, I don't want to do 8.5-4. Let's try to look at something that has as big as numbers. The 8.5-4 has a lot of decimals in it. That's why I was trying to avoid it. Only because I wanted to write these things down. Well, I'll do 8.5-6 instead. We've got 58, 52.5, 46. This is all typed in Excel, by the way. I'm just putting these in notes. 57.5, 52, 45.5, 65.5, 70, 71, 57, 54. Good Lord, I don't know if this is being so clunky today. 54, 48, 58, 35.5. This is why we're going to use Excel, by the way. 44 and 53. Okay. This is more than I wanted. I should have just made up a list. All right. So the idea here is that we want to compare this against the median being 50. So our null hypothesis here is the median will be 50. Our alternative is that it's greater than 50. So the sign test that we just did doesn't take into account, it doesn't take into account how far away things are from the median. Okay? So for example, this 52 is above the median, this 35.5 is below, but that 52 is way closer to the median than 35.5 is. So we still don't want to do it by necessarily distance from the median, because again, the median is not really a parameter of the distribution. The median is where it splits it in half, right? 50 above, 50 below. Okay? So what we want to do instead is rank these things by how far away from the median they are. Okay? So the closer you are to the median, the lower rank you have. All right? So the closer you are to the median, the lower rank you have. All right? So in this case, if we order these things, well, let's do it in Excel. I'll just go ahead and show you in Excel to start with here. There is a command in Excel that is called the rank. There's actually two of them. There's the rank average and the rank equal. So when we do the signed rank test, sometimes you can have two data points that are the same distance away from the median. Certainly possible, right? One could be two above, one could be two below. Okay. What we'll do is, instead of saying they both have, say that they're both the third closest, instead of saying that they're both the third closest and skip 4 and go to 5, what we'll do instead is say, okay, they're both the third and fourth closest, so we'll make it 3.5. That's what rank average is. So that's the command we're going to use, is rank average. Why in the world can I not remember to zoom in for you? This is an ongoing problem. I do it numerical too. Okay. All right, equals rank average number. The number we want to check is this, but not against itself. We want to check it against, what was the median they asked us to do at 8.5? It's 50, right? So we'll do the rank average. Oh, let's see. Let's not do it that way. Let's subtract the 50 first. So let's do that this way. Oh, I know what I want to do. I want to do the absolute value of this. That's my problem. Because I just want to I want to rank it by distance away. So I'm going to do the absolute value of the difference first. And then do the rank average of these things. All right, so I want to know how far 8 is relative from the median, from 0. Basically, we're just shifting everything to 0. I want to know how far 8 is relative to everything else in the list, and make that an absolute cell reference, the array, because I'm just going to copy this down and I want to compare everything else to the same array. All right, so this is just taking whatever's over here and I'm comparing it to everything else in that same list. I want to absolute cell reference this because I want to do this rank average to everything in the list. So notice I immediately see a 4.5 in there. I see a couple of things that are tied, right? That's where those halves are coming from. All right. Notice that we do have some ties, but also notice that we actually have this reversed for what we want for ranks. We want the furthest away from the median to have the highest rank. Right? And it does. It's just it has rank 1. We want to weight it where it's the heaviest, not the lightest. Right? So we need to reverse these, which is not hard to do. We can reverse it pretty quickly. But I want to show you that when it's ranking these things, it's ranking it from biggest to smallest. When we do the Wilcoxon signed rank test, we want to rank it from smallest to greatest. Okay? It's easy to fix, and it's not really broken. It's easy to change what we want. But notice here, so the 21 is the biggest number that we have, and there's 2 that are tied with the smallest, the 2's here, right? That's where we got the 14.5. Okay. So to change this around, we want to do a sine rank. Okay? If it's below the median, we want to give it a -1 in front of it. If it's above the median, we want to give it a +1 in front of it. And what was I just going to say? Oh, and then we want to make sure that these are ranked in the reverse order of what we have them now. Okay. So to fix it, I'm going to fix it actually just in the formula. Instead of doing the rank average here, there are 15 elements in my list. I'm going to do 16 minus it. So that'll make the highest the lowest and the lowest the highest. Right? We agree with that? You see what I'm doing? Then I'm going to close off those parentheses, and then I'm going to multiply this by the sine of the difference between the A1 and the B1. All right, so just to emphasize again what we're doing. This ranks from highest to lowest. That's what the rank average does. Flipping it around ranks it from lowest to highest. And we want to start with 1. That's why I did 16 minus, not 15 minus. If I did 15 minus, it would have started at 0. Okay? So the 16 minus is just flipping around, ranking from lowest to highest rather than highest to lowest. Okay? The rank average is highest to lowest. Okay, so we flipped it around. This sign here is just telling me, am I above or below the median? So basically what we're doing is we're assigning weights to how far away each sample point is from the median, the purported median, and then putting a sign on it if it's above or below. Okay? All right, so that's step 1. So let me copy this down. Okay. All right, so let's think about these individually. I'm going to go back and write some stuff down here as well and then come back to Excel. But let's think about them individually. Just like when we assigned a plus or a -1, randomly we should have a +1 assigned or a -1 assigned, depending on if it's above or below, and it should have equal probabilities, right? We agree? Now for the rankings, instead of a +1 or a -1, we'll have a +I or a -I, right? So if we think about each of these individual things, each of the individual data points, if we've got, say, V1, V2, and so on down the line, V15, I didn't order them, but I could order them, right? So the probability that VI is equal to I, if I think about ranking them in order, as from what the lowest for rankings as far as they go, from lowest to highest, the probability that you get I should be what? Versus -I. What should the probability be? What was the probability when we just did ones and negatives ones? Yeah, 0.5, right? So it should be the same thing here, right? No matter what the ranking is, when you're at that rank, it should be a 50-50 shot if you're above or below the median, right? We're putting a ranking on it, but again, whether or not that's a -I or a +I should be a half, right? We agree? Yeah? Okay. So what would be, if that's true, then what should be the expected value of VI for all the i's? It's not a trick question. If half the time it's positive I and half the time it's negative I, what should be the expected value? 0, right? Yeah, good. So the expected value here should be 0. Right? Okay. Also, how about the variance? Well, the variance well, we know that that's the expected value of x squared minus, well, sorry, it should be v sub I squared, minus expected value of v sub I quantity squared. But what's the end of this equal to? The thing I'm underlining. What's that equal to? That's 0, right? So this is just expected value of v sub I squared. Well, half the time it's I, and half the time it's negative I, but you're squaring it. So what does that add up to? It's just I squared, right? We agree with that? All right. So I know the mean and I know the variance for each of the ranking variables. What if I decided to add these up? What if I decided to add these up? Well, what's the mean of W then? What would the mean of W be? What was the expected value of each of the v sub i's? So what would be the expected value of the W? 0, right? Yeah, good. Okay, so the expected value of W is 0. What would the variance of the W be? Well, what do we do? If they're all independent, which they should be because it's a random sample, what do you do with the variance when you add them together? What do you do with the variances when you take the sum of the random variables? If they're independent. Just add them, right? So this should be the sum from I equals 1 to n of I squared. Anybody remember what that formula is? Anybody besides me remember what that formula is? This should look relatively familiar. Would have seen it in Calc 1. Would have seen it discrete. You saw it here. Yeah, you can prove that by induction. It's fun stuff. All right, anyway, there's the variance. So what am I doing? Why am I calculating these things? Well, turns out that as long as your sample size is big enough, and luckily big enough doesn't even have to be that big in this case, but as long as your sample size is big enough, the normal distribution approximates this pretty well. So you can do this by a z-score idea, where your z is pretty easy to calculate because you do z minus 0. The expected value here is 0, right? So if you calculate the sum, you take the sum and divide it by the square root of the variance there, and you get a z-score. And you can do basically a hypothesis test that way. Now, depending on which book you look at, there's, in our textbook, they do what's referred to, remember we did the continuity correction for the binomial? Where we used the normal distribution to approximate the binomial, but we did a half interval because of the fact that the rectangles were above and below the normal distribution, right? Well, you get the same kind of scenario here because really you've got a discrete distribution that you're trying to approximate with the normal distribution. But the way that the distribution falls, and you can see the picture in your book on page 446, the way the distribution falls, you end up needing to do something like a unit correction. So you always, the way the ones that are calculated in the book, you always subtract 1 off the sum before you do your z-score. Okay? That's a unit correction. Now, other textbooks don't do that. Other textbooks just do it with the sum that you get. So If you're checking your answers, if you're doing odd problems and you're checking the answers in the back of the book, they always subtract 1 off for a continuity correction. I don't care which way you do it because apparently there's a couple of different ways people do it, at least from textbook perspective. So from my perspective, I don't really care. So let's go over and see if we can do this. Back over in Excel, this was our ranks. We want to add these up. That's our Wilcoxon statistic. The sum of the signed ranks. Okay? So I just literally just added up D1 through D15. And now, if I want the z-score, I would take that Wilcoxon statistic, the 50, and divide it by the square root of, well, I can count that pretty easily. There's 15 of them, so it'd be 15 times 16 times 31 divided by 6. N times n plus 1 times 2n plus 1 over 6. So you get 1.4199, which is not going to be a high enough z-score to reject at 0.05. You can figure out the p-value for that as well, because I could do the normal distribution. Oops. Holy cow. That was the z-score, which means I had a mean 0 and standard deviation of 1. And true. So my p-value would be about 0.078 in that case. Do 1 minus that. Now again, if you were checking this against the back of the book, you would use 49 instead of 50 before you calculated your z-score, because I was using a unit continuity correction. If I change that to 49, it just doesn't change the z-score by that much. It doesn't change your p-value by that much, right? Which is why, especially when your n gets larger, it's not going to make that much of a difference. That's why I'm not that worried about the continuity correction part. Does that make sense? Again, not bad. Especially once you have that little formula set up, right? So again, just to emphasize what we did here for this formula, the rank average, again, ranks from highest to lowest. We want to rank from lowest to highest. We want low numbers associated with low values, high numbers associated with high values. Rank average does exactly the reverse of what you want. Okay? So that's why we've got this 16 minus in front. It's to reverse the order so that we get the right order for what we want for the Wilcoxon statistic. Because again, further away from the median, we want to give a higher weight to. It's the whole reason why we're doing it. Okay? Versus the first sign test that we did, just gave it equal weight no matter how far away it was. Okay? So that's what this first part here is. This second part is just assigning a negative if it's below the mean. Okay? So then we add all of those up. That gives us our Wilcoxon statistic. The fact that the sum of these, independent of distribution, by the way, the sum of those things is approximately normal. And again, the bigger the n, the better the approximation is, of course. That's central limit theorem in general, right? But turns out it's a pretty decent approximation, even if n is relatively small. So even if n is 10, the distribution is pretty normal. And that's even if you look at the book, in the book, they give you a picture of what n is 10, and it looks pretty normal. So we use the normal distribution to approximate the probabilities and do that, do the rejection from there. What we'll talk about on Wednesday is
seeing if we have two different distributions and if they have different medians. And then I'll also give you a homework assignment over these 3 sections. And I'll also change my password.
All right. Have a good one. We'll see you on Wednesday.